Tale of two brothers, open cell and closed cell spray foams, both sprayed into wall cavities. One is 4 times more dense than the other. How will they behave? The white paper lab results can only get you so far. So what's to be done about it? Answer: build test walls and throw higher than normal humidity at them. Censor the Procter and Gamble out of them. And monitor the data, compile it, and reveal it. Today, in this video, we're going to take a look at those results. Welcome to Fake News, video number 3 on vapor diffusion. Well, hello everybody. Time to get into the sauce of this week's video. We're going to get into the field performance of spray polyurethane foam and the role of vapor diffusion control. So 2 products are going to be measured in this study. This is going back to 2006. This was a groundbreaking study in Canada because we had a lot of people that had difference of opinions on what closed and open cell spray foam could and couldn't do. There was questions about studs in wood frame construction. This primarily deals with wood frame construction. Commercial buildings, the architect's going to seal them. There usually is going to be some sort of outboard rigid insulation, or the spray foam is placed closed cell to the exterior, whereas with residential or small buildings such as commercial, small dentist office, lawyer office type of thing, small building, mid-rise apartment complex or something, there was not a lot of data on wood frame construction and the use of open and closed. Should a vapor barrier be used? Should it not? And this study confirms it. So what we're going to do is we're going to rip through this as quickly as possible. If I stay too long, this video will be like an hour long. So we're going to rip through, do about 10 minutes here worth of open cell, and then we'll do 10 minutes of closed cell foam and try to get you in and out as quickly as possible. So the University of Waterloo commissioned this study with Dr. John Straub leading its research. It was a 2-year modeling of full-scale wood frame walls, as it states here, and they wanted to see in the climatic conditions of Ontario whether or not a vapor barrier, poly vapor barrier, or a secondary vapor barrier of some type should be used with open cell foam, and then what was the effects of closed cell foam. Everybody knows that closed cell foam has vapor properties given sufficient thickness, but they're not too sure about what to do with open cells. So this is how we're going to answer this. They just show you that they set up a test hut facility. They're going to maintain a constant temperature and humidity level. We'll get into those parameters here in a little bit. They used 2x6 wood frame walls. They did 2 walls of closed cell, 1 wall of open, and then they did a steel studs space for the commercial people as well to answer the question on how that's going to perform. They monitored, this is the type of construction: steel stud, wood stud, wood stud, wood stud with open cell. The foam was nearly filled in each situation, so we're talking a good 4.5 to 5 inches of material shaved off in the open cell foam's case, and then left with no vapor barrier. Open cell foam, they wanted to see in a worst case scenario how it was going to perform so they could then predict the data for how bad or good things would get based on changing the vapor barrier location. So the first thing that they did, and we're going to get into, is testing the open cell foam. We're dealing with half a pound per cubic foot, standard R value 3.5, 3.7, I really don't care, per inch. The stud cavity was sprayed to depth of 140 millimeters, which is 100 millimeters is 4 inch, 50 millimeters is 2. So basically just the full depth of the 2x6. They had a monitoring system for the humidity. This shows you the location of the sensors of where they were placing things: outboard, on the wall with a brick facade, near the sheathing, and then near the interior side. So results. July the 10th, 2006, 8 months of data was collected for the 8 walls, and this study is going to go on for 2 years. The preliminary data provides sufficient information to discuss the performance of those walls. The interior and exterior boundary conditions for the experiment were presented, followed by the discussion of the open cell foam. So let's move on to that. I want to go to, okay, here's our results. OSB sheeting on the north wall had moisture content exceeding 30% for approximately 2 months and 20% for 4 months. So out of 6 months, they were above 20%. Sheeting moisture contents were much more lower within the south wall, exceeding 20% moisture content for only a few months. When the exterior temperature increased in April, both walls quickly dried down to levels below 10% at the beginning of July. From these results, it can be concluded that the level of vapor control is insufficient for the wall assembly in a north orientation under these interior conditions, but also be representative of a wall at any orientation which was shaded from the sun during winter. During the summer, the wall appears to perform reasonably well. However, hygrothermal simulation will be used to determine the impact of different claddings' high rain exposure. So they are seeing that during the winter months, they're exceeding 20 and up towards of 30% moisture content into the exterior OSB sheeting on a 2x6 wall where they have no vapor barrier on open cell foam. Now, to my American friends and brothers, big brothers down in the United States, you're going to have to determine whether or not your state and your county calls for vapor barrier use in the first place. So maybe in South Carolina or Georgia, you're not at all seeing this, but in Iowa and Minnesota and northern Michigan, you are. You are going to see the requirement for vapor barriers. So where poly is required, or some type of vapor retarder is required, you're going to want to be using it if you're using open cell foam. Okay, so this is going to show, this chart here is going to show our no poly moisture content into the sheeting. So here's our months of November, December, January, and we're seeing that by the time February, March, we're getting spikes of over 30%, and we're getting fluctuations down as low as 20. So just what the data told us before, as low as 20 and as high as 30, and then starting to tail off as it moved into the summer months, right? This is the sheeting waste, and this is where things are going. So the interior conditions that they maintained, so where we're getting this data from is they maintained 20 degrees Celsius or 72 Fahrenheit, 50% relative humidity, result in vapor pressure of approximately 1,200 pascals, which result in a high wintertime vapor drive to the exterior. So sort of a worst case scenario. If the interior conditions were instead set at 20 degrees Celsius and 30% relative humidity, more typical wintertime values, the vapor pressures would be significantly lower, approximately down to 700 pascals, which would result in significantly smaller vapor drives. This would result in reduced moisture accumulation at the sheeting. This is further modeled and discussed in the following section on hygrothermal modeling. So they are saying that if we decrease the amount of moisture in the house to begin with, we're going to get less to the sheeting. Okay, so here is that chart. Open cell foam impact on interior relative humidity on moisture content. We're seeing here that blue is at 60% and it's spiking. So that'd be extremely high moisture content in a home, but pertinent if you've got a pool or if you've got aquariums or you have a lot of plants or you're trying to put a lot of humidity into the space to deal with exotic woods to keep them from cracking and splitting, you got to know what this will do. A high moisture content, 60%, is going to put you up into the 40% reaching sheathing. Now that's with no vapor barrier. But when you come down here to the red, 30% relative humidity is staying below the 15% mark, so much more sensible. In Canada, we just can't get into the 50s and 60s. We get into the cold weather, and that's going to form a lot of condensation in areas, doorknobs and metal brackets and windows particularly. You're just going to form a lot more condensation happening in the home because we get so much more cold outside. We can't have that much high humidity inside. So now we're getting into the vapor control strategy. So they're recognizing that open cell foam with 30 and 40% relative humidity inside should have a vapor barrier of some sort. So what are they going to do? The current vapor control strategy consists of commercially available latex paint on gypsum drywall in addition to the open cell or closed cell foam. The paint has a vapor permeance of approximately 300 nanograms. Hygrothermal modeling was used to determine the effect this paint layer would have. So what we're going to do is look at the 4 different products that they put. Poly reduced the moisture content to the sheathing and dropped it down as low as you could get it, 10 to 13%, somewhere in that range. And then using 30 perm paint, so paint that was at a fairly high perm rating, but still you can see where that's placed it at, 15% moisture content, and then 300 perm paint in the green gets it all the way up to 30%, and then finally 35% at 600 perm paint. So this plot shows that with a vapor retarding paint or polyethylene vapor barrier, control can be achieved during the winter months with open cell polyurethane foam. Even in very high relative humidity cases, safe levels of wintertime sheathing moisture content can be achieved merely by using a vapor retarding paint. Multi-year simulations were also performed using weather data from Toronto with similar trends and results. So in your cold weather climate, if you're calling for vapor barrier, if you were using BAT and poly, you should be using something like that, either a vapor block primer or paint over top of the open cell foam or over top of the actual drywall. You've got options. Or what we like to do is just put up, have polyethylene put up. And I would still say you need to have all of your seams and your joints caulked and stop the air seal, or have an air seal inside the building so that you're not having air leakage inside the walls. Now we're going to move on to the closed cell. All right, the setup for the closed cell foam. 2 walls were studied, 2x6 with 2 different types. I think that's wise because that way no one exclusive supplier could claim that they owned the data or that the data favored them the most. So put 2, extrapolate the results. They should be neck and neck. So this just shows the 2x6 wall with 140 millimeters of foam. Here we have our RSIs and our conductivity. We're dealing with 2 pounds per cubic foot foam. And then we're going to do the same 20 degrees Celsius inside with 50% relative humidity. Location of the sensors in the closed cell foam wall. Again, brick veneer, wood stud, and 140 millimeters of foam. Right, the performance of the moisture content of the OSB sheathing and wood studs is discussed for the closed cell foam in walls 7 and 8. The 2 closed cell foam products used in this experiment have a vapor permeability of 2 nanograms. The results of testing show that both walls 7 and 8 on both north and south orientations are experiencing peak moisture levels of up to 20% within the sheathing and 15% in the studs at the end of winter. Hang on, they're going to explain why. Lower than the open cell spray foam walls. Figure 10 shows a plot of moisture content of the sheathing and studs in walls 7 and 8, and steel stud 8 shows similar results. Walls on south track as same moisture levels as north, with a peak moisture content of up to 20% and drying down during the summer, although not as low as the open cell walls. The south walls experience more spikes in moisture content, which correlates to solar drives. The spray foam walls are compared to the datum wall N3, which is constructed with BAT insulation instead of spray foam. So here we have our moisture contents. But now they're going to explain what was going on. It says that upon examining the data, the moisture source for the closed cell foam walls appears to be largely from the exterior, from high relative humidity within the cavity space behind the brick, and the sheathing moisture content is less affected by the interior conditions than the conditions behind the cladding. We see this all the time. There's 2 different zones going on, right? There's your interior zone, which the spray foam guy can control, and then there's your exterior moisture content, which is what your siding envelope is going to be dealing with. The relative humidity within the ventilated cladding cavity is a function of the exterior temperature, moisture storage in the cladding, and cladding ventilation rates. Brick has the capacity to store large amounts of moisture from rain and then release it as vapor. Ventilation is provided in these walls by top to bottom vents similar to the previous beg huts, which have been shown to be sufficient to allow for sufficient sheathing drying rates. From these results, it be concluded The level of vapor control provided by the closed cell spray foam is sufficient to prevent high moisture contents during the winter months. However, continued monitoring of hygrothermal simulation will be used to determine the impact of rain and wetting events on these results, specifically in the summer months. A question sometimes raised by contractors, designers, and code officials is that the wood studs are more permeable than foam and would not allow water vapor transport to the exterior. The measured moisture content of the studs in the field testing were lower than that of the OSB. Permeability of solid wood is approximately 1.4 nanograms, which is for an 89 millimeter stud is the permeance of 16 nanograms, or for a 140 millimeter stud of permeance of 10 nanograms, which is very low and compares to the permeance of 140 millimeters of closed cell spray foam, which is about 14 to 17 nanograms, depending on application details. So, what are they saying? They're saying that when you are using closed cell foam on a 2x6 wall, the studs are your vapor barrier. You do not need to worry that the wood is a weak spot. So this was the big question that we had going around was, all right, fine, we will give you that the closed cell foam is a vapor barrier and as proven is sufficiently protecting the exterior of the home from the interior side, the sheathing level. So what do we do about the studs? Are we having to put a coating over it? Do we have to do it? You don't have to do a thing. You don't have to do a thing. The wood, along with the foam adhered to it, works as a complete assembly. All I would say that you need to do after that is where wood to wood meets and you've got a seam, put caulking in it so that air isn't going through and air carries the water. So, coming around full circle here to our conclusions, this paper presented the setup and results of an experimental investigation of the need for additional vapor retarding layers in both open and closed cell spray foam and wood framed walls used for residential and commercial occupancy. Results encompassing the first winter of testing and some preliminary modeling were presented. The open cell spray foam walls had insufficient vapor resistance during the winter in southern Ontario climate at interior conditions of 20% Celsius or 20 degrees Celsius and 50% relative humidity to keep sheathing moisture contents below 20%, particularly in north side orientation, which had moisture contents above 30%. Closed cell spray foam walls, however, did have sufficient vapor resistance to maintain sheathing moisture content below 20% for the same interior conditions. Hygrothermal modeling was performed and compared to observed results to validate the model. Using the validated hygrothermal model recommendations for the use of additional vapor retarder layers as a function of spray foam type, wall assembly, and climate can be developed. The field measurements showed that OSB and wood stud moisture contents of open cell interior vapor control layer permeance using standard interior latex paint in the order of 300 nanograms and interior relative humidity greater than 40% during the winter in a cold climate can result in dangerously high moisture contents of the sheathing as a result of vapor diffusion. Maintaining an interior winter relative humidity of less than 40% is recommended. However, because of the sensitivity of the wall to changes in interior relative humidity, additional vapor control is recommended with open cell spray foam in climates more than 4,000 heating degree days Celsius. A vapor retarding paint, smart retarder, or polyethylene sheet are better choices for vapor control in such climates. So, to my American brothers, if you are in situations where you are cold and you are required to have a vapor barrier with batted insulation, I would say be using something similar with open cell insulation. So this is your pole sheds, and this is your wood frame construction buildings as well, right? I don't think that you should just be putting open cell foam on, shaving it flush, and then just putting the drywall up. If you're in cold, the data is here. Reduce the moisture drive, lower the humidity, and have a vapor barrier on the inside. I personally like the use of polyethylene. The colder that you are, and the colder the climates, I like the use of the poly. If you are in more moderate to less severe, say like southern Minnesota, but more like Iowa, southern Iowa, and Kansas and Missouri, you might be able to just caulk the seams and use a vapor block primer on the interior finishing, like drywall and what have you. Or you can spray it directly over top of the spray foam, I suppose. Open cell can be tough if it's been shaved to get a really even and consistent layer over the cells. But if you haven't shaved the foam, say you put it into an attic or something like that to do a cathedralized conditioned attic, I think you can make a reasonable case that you can put vapor block primer. That's something that we get. There is such a thing. It's easy to get. It's basically for priming drywall, but it's for high humidity situations like bathrooms and pool rooms and hot tub rooms, where it's an actual one perm when you've put the sufficient thickness of this product on. So you can actually spray it on. It's going to go on in like a white, neutral, flat white color, and then Bob's your uncle. You're good to go. Field measurements showed and modeling confirmed that when spray foam is installed inboard of hydroscopic sheathing, moisture accumulation can occur due to solar-driven moisture from brick cladding, especially if relatively vapor-impermeable spray foam is used. Basic building physics suggests that if this moisture increase is excessive, it can be controlled by installing the closed cell foam on the exterior of the sheathing to both increase the sheathing temperature and provide resistance to vapor flow. The hygrothermal model can be applied to other climates, and future work will provide recommendations for the need for additional vapor control for both classes of spray foam installed in walls of a wider range of building occupancy and types of climates. Where I am from in Canada, this paper ended all discussion on whether or not the spray foam could be used, closed cell spray foam particularly, of course, could be used as a vapor barrier. It can, it will, it does, and we don't look back. I mean, joist ends, floor systems, under slab, you name it, interior of foundation walls, anywhere where water control is needed, that's where closed cell foam is used. So when you are going to be in contact with high moisture levels or you need to control water at a very high level, closed cell foam is your primary choice. Where you are needing some additional boost with the open cell foam is when you're dealing with what we've seen here, wood frame construction and walls, and you're going to be in enough heating degree days where the vapor drive is going to be high enough that you want additional protection. So to my American friends, I think when you're in cold and in damp conditions, excessively damp conditions like on the West Coast and East Coast, Massachusetts or Spokane, Washington or something like that, Oregon, you should be using a secondary, or I can't really call it a secondary. You should be using a primary vapor barrier on the interior side to keep that moisture drive from coming from in to out and getting high moisture content in the sheathing to the exterior. So I hope this answers the question. I've tried to keep each section to about 10 minutes. There's a lot more that we could be going over here, but I don't want to overwhelm everybody. We've been using closed cell foam almost exclusively where we are with excellent results. There's never been a problem with it. It is the premier product. We use open cell foam too. It's a tool in the toolbox. We use it on difficult to reach areas and areas that need to be overfilled, and cantilevers and areas that have got a lot of plumbing and a lot of ductwork in the way that we just can't detail it out. So we'll use that. And a lot of times we'll also spray a vapor block primer over it to give it that extra bit of protection. So I hope this answers the question. Don't breathe into the fake news that spray foam isn't a vapor barrier or that it can't control moisture or that moisture is going to be a huge problem when using spray foam. And we're going to catch you on video number 4 coming up here real soon. So comment, share, like, and subscribe. We'll see you soon.